All right, so we're going to prove that for any triangle ABC, the area of triangle ABC is 1/2 base times height, where of course B is the base and H is the height or altitude of the triangle. All right, so I just want to make a note. There are always three sets of heights and bases of a singular triangle. It just depends how you orient them, right? So, in order to prove the first case, right, we're going to try to prove that the area of a right triangle is 1/2 base times height, right? So the way we're going to do this is we're going to consider a rectangle, ABCD, and we're going to draw diagonal AC. With the properties of rectangles, we know that all of these are right angles. So this forms two right triangles, right? A, B, C, D is a rectangle, implies that the measure of angle A is equal to the measure of angle B, equals the measure of angle C, equals the measure of angle D, and all of them equal 90. And it also implies, right, that AD is congruent to BC, and AB is congruent to DC, right? So those are the properties of a rectangle. And we know that the height is just the perpendicular distance between bases. So we'll categorize this as a base and this as a base, and they both have the same length, right? Because these two sides are congruent. And then this we'll deem as the height, right? And since these are congruent, then we know these both have the same length. So the first thing we have to do is we have to show that both of these triangles are actually congruent. Because remember, the area, we know the area of rectangle A, B, C, D, we know that's just the base times the height, right? So what we're trying to show is if these two triangles are the same, right? They're congruent. That means their area is the same. So that means the area of each triangle would be half of this base times height, right? So that's the idea. So we're going to prove that both of these triangles are congruent, right? So we have AD is congruent to, so AD is congruent to BC, and we have angle D is congruent to angle B, and we have DC is congruent to AB, right? So this is side, angle, side, right? So by side, angle, side, triangle ABC is congruent to triangle CDA, right? Okay, so that means these are the same, right? So this, of course, if they're congruent, this implies that the area of triangle ABC is equal to the area of triangle CDA. Now we're going to tie in this. We know that the area of ABCD is equal to the area of triangle, right? ABCD, that's the area of this triangle plus this triangle, the one that we showed that were congruent, right? It's the area of ABC plus the area of triangle CDA. Okay? Well, since these two are, their areas are the same, right? This implies that the area of ABCD is equal to two areas of triangle ABC. And remember, the area of rectangle ABCD is base times height, right? We know the area of a rectangle is the base times the height. So this implies that base times height, right, area of ABCD, is equal to 2 times the area of triangle ABC. And if we divide both sides by this, we get 1/2 base times height is equal to the area of triangle ABC. So, as you can see, using the area of a rectangle, we're able to derive that the area of at least a right triangle is 1/2 base times height. All right, now for the second case, we're going to let triangle ABC be acute. So all of them have less than 90 degrees, right? So it looks something like this. So what we're going to go ahead and do is we're going to draw altitude. So let's go ahead and draw this altitude, H, right? So that means this is 90, right? And we'll call this altitude BD, right? And we'll go ahead and let X be this distance here, AD be X, and Y be DC, right? And then this whole distance, since we chose this to be our height, we'll let this whole distance be our base, right? So let's go ahead and say what we did. We draw altitude, BD, right? And let BD equal H, right? Now let's go ahead and let AD equal X and DC equal Y. And of course, the way this is set up, this implies that B is equal to X plus Y. All right, so since BD is an altitude, right, this implies that triangle ADB, right, ADB, and triangle CDB are right triangles, right? That means these two triangles are right triangles. And from the previous case, we showed that the area of a right triangle, right, since ABC was right, we showed that the area of a right triangle was 1/2 base times height. So, by case 1, this implies, this implies that the area of triangle ADB is 1/2 X times H, right? So the area of triangle ADB is equal to 1/2 X times H, and the area of triangle CDB, right, is equal to 1/2 Y times H, right? Because that's our base in this case, and that would be our height in that case, right? So hopefully you can see that the area of triangle ABC is the area of this triangle plus the area of this triangle, right? So, well, we know the area of triangle ABC is equal to the area of triangle ADB plus the area of triangle CDB. And of course, this means the area of triangle ADB is 1/2 XH, and then the area of triangle CDB is 1/2 YH. So of course, let's go ahead and factor out the 1/2 H in both. So we're left with 1/2 H times X plus Y. But remember, X plus Y is B, right? So this is equal to 1/2 H times B, or 1/2 base times height. So we showed that for an acute triangle, right, that the area of this acute triangle is still 1/2 the base, right? The base times the height, using our previous case that we knew that the area of a right triangle was 1/2 base times height. All right, so now we're going to consider the last case where triangle ABC is obtuse. So let's go ahead and draw our height here. Let's choose the height to be here. All right, so there is our height. And then the base of our triangle is going to be right here, right? So this is the height of triangle ABC, and this is the base of triangle ABC. All right, so let's go ahead and describe what we did. Draw altitude, BD, and let BD equal H. So let's go ahead and let's call, BD, let X equal DA, right? And B equal AC. All right, so let's go ahead and this distance here is X. So hopefully you guys can see now triangle BDA is a right triangle, right? BDA is right, and BDC is right, right? And triangle BDC are both right triangles, right? So these are both right triangles. So since they're both right triangles, this implies by case 1 that the area of triangle BDA, right? Or I guess we'll do BDC first. The area of triangle BDC is equal to 1/2. So the base in BDC is going to be X plus B. And then, of course, the height is H. And let's scoot this here. The area of triangle BDA is equal to 1/2 XH, right? 1/2 the base times the height for that triangle BDA. So we know, well, the area of triangle ABC, right? The area of triangle ABC is going to be the area of triangle BDC, right? BDC minus the triangle of BDA, right? Okay, so the area of triangle ABC is equal to the area of triangle BDC minus the area of triangle BDA, right? Area of triangle ABC is going to be the area of this whole triangle minus this piece, right? So this is equal to, so we know BDC is going to be 1/2 X plus B times height minus, and then the area of BDA is 1/2 XH. And then let's go ahead, and so this will be 1/2 XH, right? 1/2 times X, and H times X is 1/2 XH, plus 1/2 base times height, right? And then minus 1/2 XH, right? So then we have 1/2 XH minus 1/2 XH. So we're just left with 1/2 base times height. So the area of this obtuse triangle ABC, right, is 1/2 the base of that triangle times the height. So as you can see in all three cases, right, when ABC was obtuse, when ABC was acute, and when ABC was constructed as a right triangle, in all three of those cases, the area of that triangle was 1/2 the base of the triangle times the height of the triangle. So that is how we are able to derive the area of a triangle being 1/2 its base times its height.